How's everyone today? How are y'all doing? Finally Friday. Pretty good, pretty good. I feel like they definitely snuck in an extra day or two this week. Doesn't feel like Friday at all. Alrighty. So today, in the next few lectures, we're going to be looking at some different coordinate systems and how to integrate in them. And these are going to be more convenient for integrating over certain regions in R2 and R3. So first thing we're going to look at is polar coordinates. So 15.4 covers polar, cylindrical, and spherical coordinates and integration in all these. Today we're going to look at polar. And we'll probably do maybe one more example on Monday, but we'll mostly finish up with polar coordinates and then move on to cylindrical next lecture. Okay. Okay, so let's describe polar coordinates first and then see how they're more convenient for doing some double integrals and then how we integrate using polar coordinates. Okay, so so to distinguish between the normal coordinate system we use so the usual coordinate system that we use to differentiate it between the other coordinate systems, we're going to call it rectangular coordinates. And in R2, the way that works is we have an x-axis, we have a y-axis. We see how far along the x-axis in the positive and negative direction we go. So we go A along the x-axis, B along the y-axis. And if we look at the point that goes A along the x-axis, B along the y-axis, we get the point AB, which we all know how that works. That's how we label this point in rectangular coordinates. And it's called rectangular for the obvious reason. If you go A along the x-axis and look at all points that go A along there and B along the y-axis and look at all points that go B along the y-axis and look at the intersection of the two, you get a little rectangle. And in the corner, that's your point AB. So that's rectangular coordinates. And that's what we've dealt with for most of 140 and 141. Okay. But there's another coordinate system in R2 that's very convenient, as we'll see, for describing certain regions. And that's polar coordinates. So polar coordinates, instead of using labeling a point x, y, for how long you go, how far along the x-axis you go, how far along the y-axis you go, we label a point r theta. So points are the form r theta, where r, the first coordinate, gives you the distance of the point from the origin. So graphically, if we look at our point, the distance to the origin is our r. Let's pretend that line connects it to the origin. I cannot do it, apparently. There we go. And theta is going to be the angle measured counterclockwise. So if this is our point, let's call this point P. Theta is the angle measured counterclockwise that the vector OP, or let's say the line OP, or the doesn't matter, but O is the origin here. So if we look at the line from O to P, the point in question, if we look at the angle measured counterclockwise with the positive x-axis, wait, we need to go around counterclockwise to measure this. That's theta. So that it makes with, sorry, the positive x-axis. So the angle measured counterclockwise that OP makes with the positive x-axis. So instead of how far along the x-axis, how far along the y-axis, using those to describe our point, the first coordinate is going to be how far from the origin. The second is the angle made with measured counterclockwise with the positive x-axis. So hopefully you remember this. This is looked at this briefly, I believe, in 141. We talked about parameterization and that kind of thing, but yeah. Okay. So one thing to note, yeah, that's fine. So in rectangular coordinates, the name of the point is unique, right? Rectangular coordinates of a point are unique, but the polar coordinates are not unique. Right, so the reason for this is because angles are not unique, right? You can always add multiples of 2 pi to it and you get the same angle. For example, like if you have the point 2 pi over 2 in polar coordinates, right? R is 2, theta is pi over 2. You can always keep adding 2 pi to the angle or subtracting 2 pi. So to 5 pi over 2, or to negative pi over 2, oh, sorry, negative 3 pi over 2, right? We subtract 2 pi from it. And those all give the same angle, right? So that's going to be the point, as we'll see in a second, 0, 2. So this distance is 2. Whoops, let me do that over here. Of our point. And the angle made with the positive x-axis is pi over 2, but you can always go around by pi or et cetera. You can always add 2 pi to the angle, and you're describing the same point. Not super duper duper important, but we'll come on. Okay. So the important relationships between, because we're gonna have things in rectangular and we want to convert it to polar, and then vice versa. So we have the following very important relationships that you need to essentially have memorized. So if you look at xy, a point, and we describe it in polar, or vice versa, x is going to be r cos theta. So if we have a point r theta in polar coordinates, and we want to write it in rectangular coordinates, the x coordinate in rectangular is going to be r cos theta. The y coordinate is going to be r sine theta. And then if we want to go in the opposite direction, these two relationships, if we square both of these, we see x squared plus y squared is equal to r squared cos squared plus sine squared, which is just r squared. So these are the big important ones that you need to have memorized, and you will have memorized because you'll use them over and over and over again. But we also have the relationship y over x is tan theta whenever x is non-zero. Right, that's just r sine theta over r cos theta. The r's cancel, and you get tan theta. That was not as important, and you can figure that out if you know x is r sine theta, x is r cos theta. Sorry, x is r cos theta, y is r sine theta. Honestly, those are the two important ones, and you can derive everything else from those. So for example, if we have a point P in polar coordinates, is written as 3 5 pi over 6. Let's find the rectangular coordinates of P. Okay, so we know the polar coordinates. 3 is r, theta is 5 pi over 6. We want to find x and y for our point. Well, we use the relationship x is r cos theta. So r is 3, theta is 5 pi over 6. And so 5 pi over 6 is this guy here. So what is cos of 5 pi over 6? Close. So the way I like to remember these is, okay, so 5 pi over 6 is, that's why I drew this little guy over here. So 5 pi over 6 is in the second quadrant, so x is going to be negative. And cos gives you the x coordinate. And so for the pi over 6 stuff, x is going to be bigger than y. So that's going to be the root 3 over 2 instead of the 1/2. And for the pi over 3 stuff, x is going to be smaller than y. So that would be the 1/2. So this is going to be negative 3 pi over 2. Sorry, not 3 pi over 2, root 3 over 2. So we get negative 3 root 3 over 2. And then y is going to be r sine theta over 6, sorry. And then sine of 5 pi over 6 is what? Positive 1/2, right? So in rectangular coordinates, our point is going to be negative 3 root 3 over 2, 3 over 2. Okay, easy peasy. Just remember x is r cos theta, y is r sine theta. So going backwards is not something we do as often, but and a little more complicated. But let's do one example of that. Oh, well, so careful. X squared plus y squared is r squared. We're going to use that in this next one, and we will use it when we do integrals a lot. But that is a relationship that you should have just sort of in the back of your mind at all times. Okay, so suppose P is given by 3 negative 3 root 3 in rectangular coordinates, which say rectangular coordinates. Let's find out what P is in polar coordinates. Okay. So x is 3, y is negative 3 root 3. Let's find r and theta. So We know r squared is x squared plus y squared. And x squared is going to be 3 squared, which is 9. And y squared is negative 3 squared times root 3 squared. So 9 times 3, which is 27. So r squared is 36. And we usually just take r to be positive. So r is going to be the square root of that, which is 6. We almost always take r to be positive. The only time it isn't is sometimes when we have an equation in polar coordinates, but we'll cover that later. So that's our coordinate here. Okay, so theta, r is easy. Theta is a little more complicated, but not too bad. There's just like one more step we need to take. So we know tan theta is going to be y over x, right? R sine theta over r cos theta, which is so negative 3 root 3 over 3. It's going to be negative root 3. Okay, so here's the thing. There are actually two angles, if you're not counting the plus or minus 2 pi multiples, where tan theta is negative root 3, right? So we know tangent is positive here and here, and negative here and here. So just sort of sketch your point. So where x is positive, y is negative. So we're down here somewhere. So that's our point. We know we're down here in this quadrant, right here. Okay. So what's our angle theta? Then if tan theta is root 3, right? So root 3 is root 3 over 2, sorry, negative root 3. Over 1/2, right? And for what angle theta do we get that? So we get correct, we could call it negative pi over 3. That's fine. Or you could just add 2 pi to that. We could call it 5 pi over 3, etc. Either one of those is fine. They're the same angle. Okay, so here's why you need to be careful. So tan theta is also equal to negative root 3. For hang on. Yes, for 2 pi over 3 as well. But 2 pi over 3 is not the angle here, because that lies in this region up here. And we already established that our point is down here. You could use x equals r cos theta, but the same thing holds, Thomas, because you would get two possible angles in that case, and you would still have to go. That works fine as well, but you'd still would also have to refer to the y coordinate to figure out which one it is, because if you did x is r cos theta, so then you'd get cos theta would be x over r, which is 1/2, and x is cos theta is 1/2 here and also in here. And so you need to see what your y coordinate is to see which one of those gives you that. Does that make sense? Yeah, so this is not something we're going to do too much, at the risk of spending too long on this. Don't want to, but yeah. Does everyone see why it's not 2 pi over 3, even though tan of 2 pi over 3 is negative root 3 also? Because that point lies in this region up here, but we know our point lies in this region down here. So it's got to be the negative pi over 3, which is the same as 5 pi over 3. So our point is going to be r is 6. Let me write it like this. R theta is 6, 5 pi over 3. That's our point in polar coordinates. So just very extremely roughly sketch where your point is. We know our point in rectangular coordinates is, why are you doing this? There we go, is 3 negative 3 root 3, right? So x is positive, y is negative. So we lie in this quadrant here. Make sense? Okay, I've already spent too long on that. All right. So let's look at how to describe, or let's look at the types of regions we're going to be looking at using polar coordinates to integrate over. Okay, so polar rectangles I'll just call them D, whatever. So in rectangular coordinates, you said a rectangle in R2 is just the set of points x, y, where x lies between a and b, 2 numbers, and y lies between a and b, 2 numbers. So rectangular coordinates, it's a rectangle if both coordinates lie between numbers. Same thing is true in polar coordinates, except we're going to get a different type of figure. So it's going to be the set of points r theta, so in polar coordinates, such that, so r lies between 2 numbers, r1 and r2, and theta lies between 2 numbers also. Theta 1 and theta 2. So this is going to turn out, this is not remotely going to be rectangular. This is going to be basically sectors of circles, basically. Regions between circles, annuluses. So let's see what this looks like. So let's look at all the points where r equals r1. Okay, so the set of all points whose distance from the origin is r1. What is that going to look like? So I have the equation r equals r1. So the set of all points who in polar, their r coordinate's going to be r1. In other words, their distance from the origin is r1. What is that? What type of curve is that going to be? So if I say r equals 1, the set of all points distance 1 from the origin, that's going to be a circle centered at the origin of radius 1, right? So r equals r1 is going to be the set of points. It's going to be this circle centered at the origin of radius r1. Wowza. Hang on, let me try to make that sort of circular. Okay. And then r equals r2 for some bigger r is going to be the set of points, the circle centered at the origin of radius r2 for some bigger r2. So this is r equals r2. So we know the set of all points where r lies between r1 and r2 is going to lie between these two circles centered at the origin. Then if we look at theta, suppose this is theta 1. So suppose it's like pi over 4. If we look at the set of all points, r theta, where theta is equal to pi over 4, if you look at the line from the origin to those points, it's going to make angle pi over 4 with the positive x-axis, right? So those are going to lie on half of a straight line through the origin. And all those points make angle theta 1 with the positive x-axis. And so same thing for theta 2. Let's say this is theta 2. So the set of all points that make angle theta 2 with the positive x-axis, it's going to be another line, half line through the origin. Okay. And if we put all these guys together, so the set of points which lie in between those two circles and whose angle's bigger than theta 1, this first line here, and smaller than theta 2, the second one, we get this region here. Sorry, kind of hard to see what I did there, but does everyone see what that region is? If I sketch it like by itself. I'm not gonna bother. Sorry, I'm just gonna be more confusing there. Any questions about how this works? This is what polar rectangles look like. They're gonna look like Oh. Let me say sectors of an annulus. So either disks or annulus. So we'll do some examples and hopefully that'll clarify how that works. Okay, so suppose I had so let's say just the left half of the disk of radius 2. Sure. Okay. Suppose this is our region D. Okay, so this is a piece of a circle or a disk centered at the origin. So let's find the bounds for r and theta. Okay, so what is the way to think of r is what is the closest you get to the origin? So if the origin is in your region, then 0 is the closest you get to the origin. So then r is bounded below by 0. That's a good thing to remember. If the origin is in your region, then r is bounded below by 0. The furthest away we get from the origin is stuff on this outer curve. And for reasons we'll see later, this outer curve is the piece of the circle centered at the origin of radius 2. The magnitude of r to find. What do you mean the magnitude of r? So r is just a scalar here, but I think I know what you mean. But yeah. So basically, just focus on the outer curve. We'll see why for reasons later. Sometimes it's not just a number. So okay, this is we basically always take r to be positive, right? We think of r as the distance from the origin generally. So we would describe points on here, like everything on the circle of radius 2 centered at the origin, that curve is r equals 2, right? The set of points distance 2 from the origin. And that's why I would suggest you think of it like this, right? So the outer, the points furthest away from the origin that we get lie on the curve r equals 2, right? So it's good to know that r equals r whatever, r equals r naught, is a set of points of distance r0 from the origin, which is a circle centered at the origin of radius r0. Does that make sense? Sorry, I don't want to spend too long on this, but it's important that you understand this. So r is going to go from 0 to 2. Right, so we look at the points closest to the origin. Origin is in there, so r is bounded below by 0. That's always the case if the origin is in there. And then we look at the points furthest away. Those lie on this outer bit of the circle. And this is just a piece of the circle of radius 2 centered at the origin, and that's r equals 2. So r goes from 0, the origin, out to r equals 2. And those are the bounds for r. So look at the curve that lies the closest. In this case, it's just the origin, not really a curve. And the curve that lies the furthest away. The curve that lies the furthest away is r equals 2. OK, how about theta? So what's the smallest angle any of these points make with the positive x-axis? So if we're going around counterclockwise, the first points we hit make angle pi/2, right? So theta is bounded below by pi/2. And the biggest angle they make, if you keep going around, you hit 3pi/2. And so this is how we would describe this region D as a polar rectangle. Just want to say, OK, sometimes you might be tempted. Sometimes it's useful to use negative angles, but be careful. The right-hand guy always needs to be bigger than the left-hand guy. So you might be tempted to say, OK, stuff over here, that's angle negative pi/2, right? But you can't go from pi/2 to negative pi/2, right? The angles have to be increasing. So the right bound needs to be a bigger guy. Right, so you'd say pi/2 up to 3pi/2. Yes, so if the origin is in your region, then r is always bounded below by 0. It will not always be like that, though. So for instance, in this one, if we take this bit of the annulus, the origin's not in there, right? So r is going from the closest points we get are on this curve. Of course, it would do that, which is r equals r1. And the furthest away we get is this curve, which is r equals r2. OK. So really quickly, so the reason we're doing this is because, so for instance, if we have say this annular region here between the circle of radius 2 centered at the origin and the circle of radius 4 centered at the origin, this little bit of it, is this vertically simple, horizontally simple, both, neither? So for vertically simple, does it pass the vertical line test, right? Does it always hit the top curve, the top in the same curve, and the bottom in the same curve? Or does it depend on which vertical line you choose? So for instance, if I do this, top curve is piece of the top circle, bottom curve is piece of the bottom circle. But if I do this, top curve is piece of the top circle still, but the bottom curve is now the piece of the x-axis. So it's not vertically simple. Similarly, it's also not horizontally simple because if I do this horizontal line, left curve is a piece of the circle, right curve is a piece of the circle. But this guy, left curve is a piece of the y-axis now, right curve is a piece of the circle, the outer circle. So it's neither vertically nor horizontally simple, but it's very easily described as a polar rectangle. So how do we integrate over a polar rectangle? So if we have a polar rectangle where r goes from r1 to r2, and theta goes from theta1 to theta2, here's how we integrate a function over that. The double integral over such a region D of some function of x and y with respect to area. So what we do is we switch to polar coordinates. We do a change of coordinates. So our function now, we change from a function of x and y to we replace x with our cos theta and y with our sine theta. Right, everywhere we see x in the function, we replace with our cos theta. Everywhere we see y, we replace with our sine theta. And then r, we integrate from r1 to r2. Theta, we integrate from theta1 to theta2. And then dA, this is important. dA, so in rectangular, dA is just dx dy, or dy dx, depending on what order you do it in. But in polar, dA becomes r times dr d theta. You can't forget that r. So you have to multiply everything from the function where you replace x with our cos theta, y with our sine theta. You have to multiply all of that by r. And if you want to see why, they explain this in the book. But yeah, you take r from r1 to r2, theta from theta1 to theta2, and dA becomes r times dr d theta. And then in the function, you replace x with our cos theta, y with our sine theta. Okay, so super quickly. So suppose our region D is that piece of the annulus that I had here. It's a region in the first quadrant between the circle of radius 2 and the circle of radius 4. Suppose that's our D. And let's evaluate the integral over this region, over this region D of the function x plus y with respect to area. Okay, so first thing we need to do is describe D as a polar rectangle. Because it's a piece bounded by circles centered at the origin and lines through the origin, right? That's what all our polar rectangles are. If you have such a thing, such a region, it's almost always most easily described as a polar rectangle. Okay, so the points on D closest to the origin lie on R equals what? So all the points closest to the origin are distance what away from the origin? 2, right? They lie on the circle of radius 2 centered at the origin, R equals 2. How about the furthest away points on the origin? No, the points furthest from the origin. They lie on the curve R equals 4. Okay, so how about theta? So what's the smallest angle any of these points make with the positive x-axis? Zero, right? So if we're going around counterclockwise, the first points we hit are going to be on the positive x-axis, which is 0. And what is the largest angle? Well, it's pi over 2. Because that's stuff on the positive y-axis. Okay. So these are our bounds for D. And these are going to be the bounds we use for the integral. So we go to the integral. R goes from 2 to 4. Theta goes from 0 to pi over 2. If you wanted, you could do theta first and then R. It's just kind of a habit to do R first for me, but it doesn't make a difference if they're both bounded by numbers, but we'll see they don't always have to be. Sometimes R is bounded by functions, so I just like to do R first anyways. So R goes from 2 to 4, theta goes from 0 to pi over 2. Okay, so x plus y. So we need to replace x where we see it with r cos theta and y with r sine theta. So x becomes r cos theta. And then y becomes r sine theta. And then dA, remember, dA becomes r dr d theta. And so just remember to multiply everything through by r. So we get theta goes from 0 to pi over 2. Whoops. R goes from 2 to 4. So r cos theta times r is r squared. Cos theta, r sine theta times r is r squared sine theta. Dr d theta. Okay, so now it's just like a normal double integral, right? Except instead of using x and y, we're using r and theta. We're just calling the variable something different now. Just think of it like that. So when we integrate with respect to r, the inner integral, we're treating theta as a constant. So r squared cos theta becomes 1/3 r cubed cos theta. R squared sine theta becomes 1/3 r cubed sine theta. And we evaluate that from r equals 2 to 4. Okay, so 4 cubed is 64, 2 cubed is 8. So 1/3 64 minus 8 is 56 over 3. So 56 over 3 cos theta plus 56 over 3 sine theta. And in the interest of time, so we plug that in, 0 to pi over 2. Integrate with respect to theta. So cos theta, integrate becomes sine theta. And sine theta becomes negative cos theta. No, no. So it's, think of it as cos of x, right? If you integrate sine of x, it becomes cos x, right? So you're thinking of it like x in this case. Do you see why it's not cos squared and sine squared in this case? Okay. So theta equals 0 to pi over 2. And when we do that, we get, sorry, this took longer than I wanted, 112 over 3. And we'll do more examples of this next time. But any questions about this? I am sorry I went over. My apologies. But the important steps are, you look at your region, you recognize it's easy to describe as a polar rectangle. It's bounded by circles centered at the origin and lines through the origin. Change your function, replace x with our cos theta, y with our sine theta. Find the bounds for r and theta, and then dA becomes r d theta. And that's how we integrate in polar coordinates. Okay, so we'll do more of this next time. We'll look at some more complicated examples. But yeah, that's it for today. Have a great weekend, and I'll see you guys on Monday.